All right, so we're gonna look at generator, and then after that we'll look at the transformer. But both are applications of what we've already seen. So anyway, let's get to it. So it's just helpful to see a picture. So a generator, the way you want to think about a generator is that you already have a coil here. So try to draw my three-dimensional picture, and then I actually have a better picture we'll look at. We have this coil. This coil is not connected to any circuits or anything. It's just a square coil, and it does have these little rings here just to connect it. And this goes to some let's say a light bulb. Okay, so there's a magnetic field here, and I'm just going to draw my magnetic field going like this. Okay, so I have a magnetic field going through this coil, and I have, of course, let me draw my normal direction. Let's do it right here. Okay, there's n half. Okay, so if I'm not moving this at all, I just have this coil just sitting here at making some angle. I guess I could call it theta. Okay, some angle theta between the magnetic field and the normal direction. All right, so I do have a flux right now. So remember, flux, magnetic flux is BA cosine theta for the case of constant magnetic fields. And indeed, we have a constant magnetic field here. Okay, now if I start to rotate this, let's give it some angular velocity here. Okay, I start to rotate this, then as I rotate it, that angle is going to be changing. And it's going to be changing according to this angular velocity. So the change in that angle, so theta, your angular position would depend on the angular speed times the time. So this is going way back to when you're looking at rotational motion, but you could figure out that angle depending if we know what is the angular velocity and the time, assuming that theta was 0 to begin with. Okay, so if our initial angle is 0, then I could replace my flux here, or replace the cosine theta with cosine omega t. Okay, so that now, when we do that, if this is changing, if this angle is changing, then we are seeing flux is changing, right? And if flux is changing, then Faraday's law says we're going to have a voltage. So my voltage here, according to Faraday's law, is negative d phi m dt. So that's negative d, and that's going to be b a cosine omega t. Okay. All right, so we take the derivative here, b and a, those are constants. The strength of the magnetic field is changing. The area itself of this coil is not changing. What is changing, though, is that cosine, right? So we're going to take that derivative of cosine. Our derivative of cosine is negative sign here. So we get an EMF of BA sine omega t. Okay. Now, what's going to happen here is that in a usual generator here, you don't just have one coil. You're going to have multiple coils going through this. Okay, so you have all these coils kind of rotating, this n number of coils. So our total flux will have to increase by a factor of n. So I'm going to put n here. So EMF gives us, I'm going to call this thing here, and the NBA there, I'll call it Emax, my maximum voltage times sine omega t. Okay, so we're Emax equals NBA. Okay, so what this generator is going to do is give us a voltage. It looks something like this. right? Where the maximum value here, and I guess the minimum value, is the NBA, or E max. Okay, so this is where we get our AC power, which we're going to talk about in the next chapter. So your book, chapter 31, we're going to skip and we're going to go back to kind of more closer to the end of the semester. Our next chapter we're going to look at is chapter 32, and chapter 32 deals with circuits when you have this kind of voltage. So it's an AC voltage, an alternating current voltage. So this is where we get all our electricity from. What the generator is doing is taking some kind of mechanical motion, right? You have something rotating this, something spinning it. It's usually some kind of gas motor or something like that. You have some kind of mechanical means to rotate it. As you're rotating it, that energy is then translated to an electrical energy or into a current. Okay, so we're using Faraday's law there to produce electricity here. Okay, so we get our AC voltage like that. Okay, now this is a little different than the motor. We talked about the motor before. The motor, in order for a motor to work, you need to start off with a coil that has current, and that motor then changes electrical energy into mechanical. Right, the whole point of a motor is to get something to spin, while the whole point of the generator is to produce electricity. So they're kind of the opposite from each other. And while both of them have a magnetic field, that magnetic field functions in different ways. For the generator, the magnetic field is, we're using the flux of the magnetic field, or the flux the magnetic field creates, to give us a voltage. For the motor, we're using the magnetic field to give us a torque. Okay, so very different, although they're very similar, kind of very similar setups, very different. Okay, so what we will see here as far as this light bulb, you'll see this light bulb glow here, and it will get dimmer, then get brighter, dimmer, brighter, as it'll follow this curve here. So that is how generators work. Oh, I was going to show you a neater picture of this. All right, so this is what a generator does. Converts mechanical energy to electrical energy. And here's that neat picture I was talking about. So you have here's that coil. The coil doesn't start off with current. Okay, there's no battery here, right? There's nothing producing that current. Once it starts to rotate, then you get the EMF, and then you get the induced current here, and that induced current will flow through this resistor, right, or whatever circuit you have here. Okay, so as it starts to rotate, we saw that it's going to give us a sine function, right? And we saw how that comes about. Okay, so it's just a neater picture than what I drew earlier, so you could kind of see how this is set up. Okay, and oh, I forgot this omega. Nobody caught it? Yeah, I forgot to write this omega there. So I'm glad I went over this. Let's go back to that, fix that issue, right? So my bad. So when you take the derivative here, we're taking a derivative of function within a function, right? So we got to do a chain rule. All right. So I forgot to do chain rule, guys. Omega, there you go. And so this would be NBA omega. And you know what? I have it in my notes too. I don't know why. I get carried away when I start doing it on paper and forget to check my notes. Oh well. Yeah, I forgot to put the omega. So application of Faraday's law, we saw the generator. Let's do application in the transformer. Okay, so for the transformer, the setup, again, I'll do a quick sketch of it. So let's say we had an iron core. Okay, so I have this iron core here, and I'm gonna have two circuits. So actually, let me move this a little bit because I'm gonna run out of space. So I have a circuit right here. So it's gonna be an AC circuit. Whenever you see that symbol, kind of like that curvy, almost sine shape, it's telling us that we have an AC circuit here, AC power supply. So I have this goes around here. Okay, so we have several coils going around this. I'm gonna call this the number of coils here. I'm gonna call it NP. So this is called my primary coil or my primary circuit. Okay, that's the one that's kind of providing the electricity. And I have another circuit here on the other side. Let me do this in blue here. I have another circuit where this circuit is just connected to a resistor or some kind of appliance or something. And this goes around this as well. Okay, and I'll call this NS. Okay, so I have a primary circuit and a secondary circuit. All right, so as I start to have a AC power supply here, what we're going to have is we're going to have flux being created here. Okay, so all this, as I have these coils going around, a flux is created like this. All right, and if I have flux going through those coils, I have a Faraday's law tells me that we're going to have a EMF on the, let me do that in black. EMF in the primary equals to the change in flux over change in time. But we have a number, so many coils there, so we have to multiply by the number of coils. Okay, and I put my negative there. And then on the secondary coil, kind of the same thing. I have a number of turns times dVB over dt. Okay, now by connecting it to this iron here, whatever flux I have going through this coil here, it's going to be the same flux I have going through this coil. Okay, so I have all this flux going through here. The iron here is going to ensure that the same magnetic flux I have going through here, well, different from number n, but this is going to be the same. So the change in flux over time for my primary is going to be the same change in flux over time for my secondary. So if these two are equal, I can kind of set up a ratio here. Let me divide this equation by this equation. Okay, so I'm going to divide my EP to the opposite side here, divided by ES. And that's going to give me NP over NS. Okay, or maybe rearranging. Let me solve for the primary, for the secondary coil. If I solve for the voltage in the secondary coil, I get NP over NS times EP. So what that result tells me is that the voltage created in that secondary circuit is going to depend, it's going to be greater than or equal to the voltage in the primary circuit, depending on the number of coils, right? So let's look at a couple scenarios. Let's say that NP, I have more turns on the primary side than I do on the secondary side. So NP is greater than NS. Okay, in that case, this is going to give me a higher voltage in the secondary circuit. Okay, so this is known as it's called a step-up transformer. Okay, so what a step-up transformer does is it increases your voltage. Okay, from one circuit to the other is going to step up that voltage, and again, depending on that ratio from NP to NS, that could be a factor of 10. It could be a factor of 1,000, because we could put a lot of coils on these iron cores here. The other scenario that we could do is, let's say NS is greater than NP. Oh yes. No. Let me see. I saw for ES. Oh no, you're right. You're right. Thank you. I appreciate that. Always took my math here. So yeah, I went too fast. So if I solve for ES here, so I'm looking up here. If I solve for ES here, yeah, I do get NS over NP. Oh, no wonder that didn't make sense there. Okay, so let me change that. So I get, I'm down myself. So NS over NP. Okay, which means that we're not looking at step-up transformer there. Let me erase that. Okay, so let's do this again. If NP is greater than NS, so we're going to get a fraction here or a decimal here. So that's going to mean E. Let's just do it again. Okay, so NP is greater than NS. That means ES is less than EP. All right, yeah. Okay. Now, and the other scenario, if NS is greater than NP, that means ES is greater than E. Okay. So let me actually make that a little bit neater here. Okay. So, so like I said, it does depend on the coils, right? Which coil is going to be greater, and that will determine whether we have a what's called a step-up transformer or a step-down transformer. If the secondary circuit is lower, it's called a step-down transformer. Okay, which is this. And then if the opposite is true, if we have more turns on the secondary circuit, it's called a step-up transformer. Okay. All right. So where does this come in handy? Well, it comes in handy quite a bit. Let me show you this. All right. So we talked about this, and actually, there's kind of some interesting history here too. Kind of goes back to kind of like the whole Edison versus Tesla thing that kind of happened in what was it, the 1800s? So voltage. The problem with AC circuits is that the voltage was incredibly high, which made it pretty dangerous. It was good because it could travel further distances, but in traveling further distances, it was too much voltage there. So Tesla had to bring this voltage down so it could actually be used, and it wouldn't be too dangerous, to have kilovolts come into your house. So this is why the transformer was there. So the transformer does both things. It increases the voltage when we need it to, and it decreases the voltage when we need to. So we already talked about this. So I'm going to kind of speed through this. So you can see, right, NS over NP. NP is greater than S, we get a step down. NS is greater than NP, we get a step up. That's what we discussed on the whiteboard here. But what I want to show you is this picture. I think it's next. There you go. So where does it come in handy? Well, we couldn't have modern day electricity without this transformer. So you have the power plant, which is producing all this electricity. It goes to this kind of this substation here. That substation, we have all these step-up transformers in there, which takes it from 25,000 volts, which is already pretty high, to 500,000 volts. And we need it to go to such a high voltage because it's going to travel such a long distance, right? With longer distance comes more resistance in the wires here. And so we need to make sure we have a good voltage to send that current such a long distance. So we send that current, this is a kind of those lines that you see in the freeways, kind of when you're just kind of driving, kind of maybe on a road trip or something, and you see these huge towers carrying these wires. This is the 500,000 volts. And now it goes to a neighborhood, to a substation here, and we got to bring that down. So we got a step down transformer here, bring it down from 500,000 to 7,200, and then that goes into neighborhoods and just goes right outside our homes here. And before it goes into our homes, we bring it down again. Right, have another step down transformer and bring it down to 120 volts. Okay, or maybe you could get 240 depending on your house there. Instead of having all this voltage from here go directly to our homes, not only would that mean that you would have to have a power plant in pretty much every block, but that would also mean you have such a high voltage going to your home. So the transformer really revolutionized how we get our electricity here. So just kind of practical application of where do we see this? Well, step outside your home, look up. You see in the cables there, you should see the transformers. Okay, so let's go back here. All right, so that's those are the applications for Faraday's law. There's a couple of other applications that are pretty interesting. You could look at eddy currents, which is like currents within conductors, and how that works with metal detectors is pretty interesting. We don't have time to go over that, but your textbook goes over it. But that's all we're going to look at for applications. We're going to take a short pause here because we're going to start talking about something different here, which are inductors, and kind of dabbling into AC circuits. So let's take that break.